Hey everybody. So this is a research paper called Adaptive Chunking Improves Effective Working Memory Capacity in a Prefrontal Cortex and Basal Ganglia Circuit. Completely different paper than I would normally cover. It's sent in by a viewer. I'm glad that they sent it in, which is why I'm covering it. And it's produced by Brown University and it's published in the eLife Sciences Journal. This particular research paper, so off the top, I see like people fall into two camps when it comes to kind of how AI is progressing and whether or not it's actually like advancing or we're hitting scaling limits, right? There's kind of people think like it's hit a brick wall, and then other people think like, oh, it's like advancing like crazy, right? Like gangbusters. And then it's just one of those two camps overall. And then so where and how exactly does that schism come about, and where does that schism come from? And then so the bottom line within that is that when it comes to scaling AI overall, we're kind of scaling it in a unique and a different way than previously done with regards towards computer scaling overall, right? A lot of the scaling is less linear with regards towards the scaling, but nevertheless, it's still improvements and scaling the performance of the models overall, right? And then so within that, this is a very perfect and great example of that. And this paper is all about working memory and then working memory capacity, right? And then so how exactly does this lead into and correlate with like scaling AI and scaling models and computers, et cetera, overall, right? Well, so what this paper and this research paper shows is that it's possible to get more performance out of the same amount of memory, just depending on how you structure and utilize the memory overall, which is like the bottom line significance of that, right? And then so those performance gains are scale. So if you can get the model to perform 30% more efficiently, that's a 30% scale. It's performance increase, no matter how the scale comes about, right? It's still increasing the scale there. So then how exactly and do they get that performance increase, and what exactly does that look like? And so the interesting thing and how this paper breaks it down to me is, so when it comes to working memory, and then working memory we'll call like your ready, like available memory, right? Like you're thinking about a task, how much memory do you have to think about the task? And then within that, the very first thing that they prove is that like for both like humans and AI models, that it's more of a computational equation. Like, so it's a hard limit, right? So I'll just use very simple terms and I'll simplify this like very significantly, right? So let's say that you have a bowl of fruits on the table, and then so knowing that it's two fruits, like it's a banana and an apple, like, and then just memorizing banana and apple, very easy, right? It would be very like not hard in order to do that. Banana and apple, right? I can recall that very significantly and very easily. But then so if we move to, let's say, 5 fruits on the table: banana, apple, grape, lemon, and tomatoes, fruit. So I've already forgotten all 5, right? And then like just within that, and then that's because of the cognitive and compute's ability to like store these values. There's a fixed amount of storage capacity within that, right? But then so this paper and what it delves into is, okay, so then you fill up that storage capacity. We've reached the limit, right? So 5 fruits is the limit within this particular experiment. Then how exactly does the brain overwrite that, right? Does it just throw out like some fruits? Is it just like a banana, apple, and then I forget tomato? Like, or is it like the more realistic answer, like a more of a, like a probabilistic blend, right? And then so within that, what exactly constitutes and how exactly does that probabilistic blend occur and what are the dynamics around it. And that's what a lot of this research paper dives into within that. And then so they call that particular aspect of working memory chunking. And then so a good example of chunking, let's go back to instead of a bowl of fruits on the table, it's a shopping list. And then in the shopping list, I have categories of, so I have I want bananas, apples, grapes, and pineapple. And then I want bread, and then I want some dessert stuff. So I want like ice cream and cake and cookies. And then so within that, what I like the way to chunk that is kind of how I just instantaneously did, right? Like our brains are very accustomed to this chunking mechanism and this chunking model, which is rather than looking at the holistic grouping of the items. So the very first thing that you want to do and you try to do is try to put them into categories that make them lossy, essentially, right? Like so the very first category was fruits, and then so I don't have to remember every single fruit. I remember the category of fruits, and then within that, once I remember the category of fruits, I can, once I'm at the store, remember the fruits that are within that. Oh yeah, okay, so I need to go to the fruit aisle, and then once I'm in the fruit aisle, then I need bananas, apples, grapes, and pineapple. And then I can chunk that back together, right, and piece that back together from the bigger chunks. And then same thing. Oh, I'm in the dessert aisle. I need to get cake, cookies, and ice cream. And then it's so I don't have to remember and memorize cake, cookies, and ice cream, and then I don't have to remember and memorize the individual fruits. It's just memorizing and chunking into those categories. And then that ability effectively increases my working memory capacity, right? Like within that, I just I named off and I remember like more than five and the categories very easily and very simplistically just via this chunking method, right? And there's a lot of this is all known throughout human memory, how it works, etc. Like pneumatics and all of that goes into memory. Like this chunking category. Remembering things like as a symbolically, all of that is goes into this kind of lossy memory system, right? And then so from there, we know 100% then that this lossy memory system exists, this chunking memory system exists within humans and biological organisms for memory. And then so the question is then can we develop a structure for computer models that would allow for that same type of process when it comes to working memory. When it comes to working memory for computer models, they typically work the exact opposite. Like so, if their memory is full, they have to cut something from the memory, just flat out, right? Like that's they have to remove something from the current memory and override it in order 100% in order for to fit something new within that. So it's an overwriting process rather than this chunking process, right? And then so the question becomes then, can these models do that chunking process rather than the overwriting process? And that's what the majority of this paper focuses on. And through their methods, they prove out that yes, the model is able to do this process and it can chunk out and operate as a chunking memory model. And then so this is essentially the model that they build out. And then this model that they build out is based off of the basal ganglia and the thalamus in the human brain when it comes to these functions of working memory. And then they're just essentially reconstructing those into what to me from a computer science perspective is almost like a transformer. Are these very similar to transformer and or perceptron architecture, right? Where you're just building these. I can see it's definitely a deep neural network, which is what they're trying to go for within this, right? And then so it's kind of cool and interesting to me how this works. And then so you can see here's the essentially the difference between the two memory types, right? So slots versus slot based. And then so their approach that they develop is this hybrid between those two methods called slot. They call it slot-based chunking. And then so slot-based chunking. So slots would be, let's say that you have coincidentally 5 categories, right? And then so this one, but you only have 3 that you can hold. So you have to just eliminate 2 if you have 5 in there, right? Flat out. But then, so what this slot-based chunking allows for is, so, okay, let's just eliminate 1, and then we'll probabilistically blend 2, so you actually have 4 in there. And then that's kind of just how it's able to piece that out and work within that. And then, so on the computer science end, on the AI end, how are they able to do this on the models and tease this out of the models? Very simplistically, utilizing reinforcement learning. But then on a deeper level, as I kind of alluded to and mentioned, they're not utilizing transformer architecture within these models, right? These particular models that they're working on within this and reviewing and evaluating, they're spiking neural networks. And I've made a few videos on spiking neural networks on my channel here before. But so that's the models that they're evaluating. They actually give all of the code here for the models, like their base model. So this is the biologically based neural network simulations of the brain, written in Go with a 3D GUI powered core by Cogent Core. And then so they release all of the code here, and then so they call it the emergent neural network, and it's an emergent neural network simulation framework. They provide all the toolkits. Again, it's like 100% in Go, and they explain it that they couldn't provide it. Like if you look through like their older implementations of this, like the somewhere in here, like the revisions, you can tell like here, their initial revisions were in Python, and then like somewhere like last year they updated it all to Go, and then made it better and expanded it out. And then so for reasons that they state up here, they can't. Yeah, the single clearest motivation for using Go is that Python's too slow to implement the full computational model. It can only serve as a wrapper around the backend code, which is often written in C or C++. And then so by contrast, Go can implement the entire model in one coherent language. And so that's why they release it in Go there. But so here it is, all of the code. Last updated a few months ago, and then this project has been going on for a while. It's got lots of contributors overall, and then so cool project to see if you want to play around with spiking neural networks, and then especially like with different memory configurations and biological-based memory configurations. Very specifically, this is the repository for you and the research paper for you. So I'll leave a link to both this research paper, Adaptive Chunking Improves Effective Working Memory Capacity in a Prefrontal Cortex and a Basal Ganglia Circuit, as well. And then from here, you can link to very directly the Colab or the GitHub repository that they list out here for all of the code. And if you like this type of content, please like, subscribe. Thank you very much.